Hello, my name is Kobie Jones. So I'm going to be talking about convolutional neural networks. So why am I talking about convolutional neural networks? I think it's the best place to start when trying to dive into deep learning and machine learning, or just like anything in like that, in the AI or machine learning or deep learning side of the spectrum, just because you don't need a whole bunch of data to actually get started with it. There's a whole bunch of sets online, and also it's easy to actually start working with like the actual data. So what our CNN used are for? Mainly image processing. So image recognition and obviously images and videos. And also mainly people would tie them into natural language processing and other networks. So like they'll start with like their image processing, and they'll pass it forward in like a feed forward network, and they'll pass that data off. So, oh wow, his name's spelled wrong. Well, Yann LeCun, he's pretty much the innovator. In 1998, he sort of started the deep learning and machine learning craze again. Convolutional neural networks was pretty much the breaking point in actual the innovation, or like the moving forward of like the actual field and making it more popularized, because beforehand it was like very time consuming. The data, or like the time and space capacity that it actually took to run these models was immense. Actually, let me fix this because that's just embarrassing. That should not be like that. There we go. But yeah, so what is a convolutional neural network? Let's look at just like, because I'm looking at the model. So a lot of pictures will show the top one, or like when you're first starting, you see like the top one, and you're like, what is that? All I see is the image, convolution, fully connected, and you see all these neurons and all these different things, and it's scary. It's hard to actually get into. You actually have no clue what's going on, but it's not that hard. Like just the simple code below is pretty much the same model that you see above. So it doesn't take that much, like just like a little bit of research, and just like getting started allows you to actually go from being a beginner to actually being able to start creating your own models and trying stuff on your own images and other things like that. So what is convolution? Because that's pretty much the name of the whole thing. So convolution is sort of like this, it's matrix multiplication. So every single point you're pretty much multiplying. Actually, this is a bad zone here. So like you have, so pretty much you have your like your image data. So you can think of like all these like points, different numbers, as actual image points. And then you have their kernel, which is sort of like an activation map. So when you're actually doing, when you're actually working with a model, you start at a pretty much an image. So let's say you have a 28 by 28 image, or you have a 192 by 192 image. And the problem is you want to get the important information out of that image. However, if you keep on trying to pass that data on, and you're trying to find all the like important features in that image without actually reducing the size of the image, you're gonna have, you're pretty much, the space that you're gonna need for like to store all the data points that like store that like the important information is gonna multiply so swiftly that you'll actually run out of like space or capacity on your computer. And so this is why convolution has revolutionized, or just like the thought process of using it is revolutionized machine or deep learning, especially for image processing. Because what you'll do is, first of all, you'll take an activation map, or what they call kernel. And so pretty much what convolution will do, it will pretty much go over the entire thing, and at each point it will pretty much multiply it by like the number in the kernel. So let's say you have like this, the top like corner. So if you had like the 627 1 2 3 0 1 4, and you match it up with the kernel, you'll pretty much only get the important values from that. So you'll get certain points that the kernel is actually looking for. So in that case, you'll get 6, 2, 2, and 1 when you do the multiplication. And then you add it together. If we go back, I think, yes. So as you see here, you'll take like your top corner and multiply it by the top corner of the kernel, and you'll just keep on doing that, and then you'll add them all together at the end. So it's sort of like taking the dot product, where you start at you pretty much take a vector and then turn it into a scalar value. And then you pretty much are reducing the size based off of your stride, which is stride is sort of like how far you'll walk over the thing. So if instead of just going from, let's say you start at the 6, 2, 7 quadrant, so that by 3 by 3, if you have a stride of 1, instead of going to the 2, 7, 4, 1 and making a 3 by 3 going down there, you'll skip to the 7, 4, 2. And so by doing that, you're actually reducing the size of the image, which is pretty much sharpening the image, because you're still getting all the data points from those spots, but you're just condensing it. And so as you're doing machine learning, you'll have a whole bunch of different kernels. So you'll just keep on going over here and do this convolution layer, and you'll get pretty much the same image, but it's just it's sharper because all the data points are more condensed. And so you're technically losing some points, but you're getting you're still keeping most of the important features, and you're actually highlighting them pretty much in your data set. And then also, after that, mainly what people use after that is the max pooling layer. And so the max pooling layer is another way of dimensional reduction, where pretty much it's the same logic as when you're actually taking the convolution layer, where you're taking that 3 by 3, but instead of just like adding them together, you're only taking the maximum value in each spot. So you're taking pretty much the most important feature and passing that through. So like in the top corner, you see that this data gives you 6 in the top corner, and then you get a 7, and then 3, and then continuing like that. Activation functions or transfer functions will be often placed after or part of the convolution layer. So this is just pretty much to normalize your data, to say the least. So you don't want to have points that are super extraneous in like the positive value, or you don't want something in the negative value, and then you don't want a 1, because those like super huge numbers, if you are like that the kernel could create just from doing that operation, could be extraneous to like all the other points, so those other points could be lost. And that over like bearing like number like 1,000,000 would be pretty much be taking over the data set, where you will actually lose the 1. So that's why will apply an activation function at the end, so that we don't actually lose those features. So pretty much sigmoid will pretty much turn those data points from a value between 0 and 1, where smaller values will become 0 or be closer to 0. So numbers close to negative or negative numbers will be close to 0, and then the bigger numbers will be approaching the value 1. And then ReLU is another way to do this. It works a little bit differently. Instead of actually, it pretty much punishes values that are super small or below or negative, because they think that they're not influential. So they just say that they're 0 instead of calling them negative, because that can also influence the thing. Whereas it actually allows the strain or like super large values and pretty much says, oh, well, this is very important. But it says that negative values have the same significance as pretty much the value 0 on the scale. And then softmax and image classification will be it will be what actually tells you the results and what the probability that it thinks that that certain point is the actual classification you're wanting. So whether something's a cat versus a dog, and how confident it is a dog over a cat, or however many other images that you have. And then lastly, you have your optimizer, which calculates like the loss. So how how far it was from the right predictions versus like the wrong. It sets and changes the learning rate, so that's how it approaches like the right results, or like goes to that minimum loss. Your learning rate is probably the most important thing that you can actually set in your model, especially with your optimizer. Usually you don't have to actually deal with this because your optimizer will usually handle it. You'll give it a default, so like 1 is a fast learning rate, where like 0.001 is a very slow learning rate, because like what you're trying to do is it's sort of like taking so through your network you'll pretty much have a whole bunch of functions, so y equals mx plus b. And so what you're trying to do with your learning rate is you're trying to optimize those slopes and your constant values, so like your b values and then your slope or gradient in this case, and you're trying to actually make them or fit them to like your actual model so they actually represent your data. And so your learning rate, what you'll do is, the learning rate is how fast you actually change the actual slope, or to change the value to actually match your data. And so it's very important that you actually set it at a rate that actually works with your model, because if you are actually, if your model predicts like wrong answers and you have a fast learning rate, you're going to overshoot the minimum, or you're just going to completely just be going the opposite way, because it actually will it'll reward bad values or bad behavior pretty much, because you have a fast learning rate, so you'll just keep on jumping over it. And then also it can make you become in an infinite loop, because you're trying to like find that minimum like point of loss and actually like fit your model. So like if you have a fast learning rate, you can just jump over the minimum and you can just be in like an infinite loop where you're like, oh, it may be over here, and it's like, no, I can't find it over here, so let me go back the other way, and then you'll just keep on missing it over and over again. I sort of glossed over that, mainly because there's like a lot of mathematical stuff going on in the background, and so I wanted to sort of show you talk through examples of just like a generic set, which would actually help you like learn exactly what a model is and sort of how you actually can make one, and then how like everything works all together. So this is pretty much an example of the MINT data set. So it's image recognition for numbers between 0 and 9. And so what you're trying to do is classify numbers or from 0 to 9. And so you have 9 things that you want to try to find, or you have 9 examples of images from this data set that has 650,000 points. And so each image is 28 by 28. So as you see here, we specify these image rows as 28 by 28. So if we just load the data, this is just because of, like I said, doing machine learning takes a lot of CPU or actual computing power, and a lot of your computer's RAM and memory to actually do. And so I added this just so that my computer, or once I stop, like my model stops learning, it will just pretty much say, okay, this is pretty much the best I'm gonna do. So like you can make changes after that fact. So whenever you want to train a model, you're going to want to set up your train test split. So you want to train your model on some data, and then you want to test it on like data that has not been seen, so that you're not actually just memorizing the like data beforehand. Because like if I just gave you like, it's like studying for a test like the night before, you may like learn all the material, but you don't retain it. You don't actually know like all like the details. You only know like that data set or like how to do those things. So that's why you want to like mix your data, test it on some, or like mix your data, train it on some, and then test it on others that it has not seen. So so like the model will actually learn new stuff as it goes. So these are just converting it to this is just, oh yeah, I also didn't mention, this is in Keras, this is in TensorFlow. So this is a Python deep learning software. Yeah, probably shouldn't mention that. So, but it uses the TensorFlow backend, or I'm actually using the TensorFlow backend. So pretty much this will pretty much say what are the right answers, and then what are like the actual values that you want to train it against. So like you're pretty much telling the model, okay, this is what you're aiming for, or like this is what you should be aiming for, but here's the data that you're going to want to test it on. You set up your model just by doing sequential, because we're just going to like run straight through it. So it's going to go from here to here and off forward. So this is where we start adding like the convolution layer. So convolution, you see here, we're going to have 32 data points or nodes in here, or I guess weights. We're going to have a kernel size of 3 by 3. So this would be your activation map or kernel that I was showing you before with like the ones and zeros, or however like the optimizer will actually pass in later. Usually you'll specify like the range by normalizing some like data set, and it'll start there. But in Keras, it actually takes care of everything for you, which is nice. You have an activation function. In this case, I'm using ReLU. And then the input shape is just this, pretty much the size of like the image, which is 28 by 28 at the start. So that's pretty much it. That's all you had to do to set up a convolution layer. You didn't have to do any of the math here. It makes it very simple and easy for you to actually do. And then you have the model add again. You add another second one, which is your second convolution layer, 3 by 3 again. And then you just do ReLU again, apply your activation function. And it's pretty much just rinse and repeat there. Where you have max pooling, where you have your pool size of 2 by 2, which would be your kernel or activation function. You don't actually have to set your stride function as you do in other languages, because in Keras it'll default to your pool size, which is 2, which is nice. Also, just to mention, this type of model, because I forgot to mention it earlier, this type of model helps with actual overfitting, just because of you're not actually looking for you're not looking through like the image itself. Every single layer, you cut the image into smaller pieces, so you're not actually looking at the image, you're looking at common details in that image. So when you're actually putting back together the image, the common features that you would find in like a cheetah or a leopard that's like standing upright versus the image that is like backwards would be actually, you would find the same common like generalities, like the face and like the teardrops in the eyes. So you actually don't even have to prepare your data that much. All you have to do is make sure that your image sizes going in are the same size, so that you actually, as you're going through, your like input and output values through each of your different layers will be the same. So this is why I actually love convolutional neural networks, is because it's super simple to actually get started. All you need is like whatever like the data that you want to train, you just need to make sure your images are the same size, so that it actually propagates through like the your model like through like the same sizes, and so like you can actually put it all together and train it on like the same thing, and you're pretty much good. It's already pretty much dumped to you through like the mathematical functions behind it. And so pretty much as you go through the model, the last thing that you have is pretty much your activation softmax, which will actually tell you or make the prediction on your set, where it will pretty much say, okay, I can predict this to be a 9 or a 3 or a 5 in that case. And obviously then you apply your optimizer. In this case, I'm using Atom. There's actually a lot of optimizers that you can find online. On my last slide, I actually gave a link to like explaining the mathematical functions behind like the optimizer and how it works, and how it uses back propagation to like change the slopes, etc. But yeah, most of it's already done here. You just need to apply your learning rate, And in this case, I use 0.01, and then you're all set. And then finally, you just fit your model to your training data, and then you validate your data through your testing data. Epochs is how many times you want to see like each data point, or how many times it should go through it. I think above I said 12, so I want to see like each data point 12 times. So that's how many times it will run through the model and repeat the process. And then your callback is sort of just saying when you want to stop, or a function that you want to apply while your model is running. So, does anybody have any questions so far? Probably should ask this.
So, what's the batch size?
So it's sort of like how many images you want to apply at a time, and then it'll find a new batch like right after that. So you're not actually going through like every single image. It'll like randomize like the images, like 128 images, and it'll be like, okay, I'm done with this. And then it'll apply the same process where it'll take another batch of 128 random images and pass that through. So it's not actually just, so you're not just saying, okay, I'm not, or like in this model, I'm not saying just go through like my training set and just in total, like just each one individually and just train it on that. I'm saying take 128 random images from my training set, train on that, and then look at another random sample of 128 and keep on like changing results, or like changing results after those 128 data points. So I'm sort of like optimizing it on the fly through the training data set. Any other questions?
I let you go.
You guys have any questions? All right, then I will move on to the TensorFlow example of the same thing. So this is TensorFlow. It's the same pretty much model. Nothing's like the same data set. It's a little bit different because you actually see that you have to apply like the strides and all the padding and like the weights inside of here. So first of all, I pretty much make functions, or you'll make functions for your convolution layer. I mean, you don't have to. This is just convention, or just to make it nice, just like categorize like where the code's actually happening. So pretty much you'll have to set your strides. In your convolution layer, your weights are here, your input size, so that'll be the amount of weights, and then your output. And then padding the same is just so that you don't actually put like extra zeros at the end. This is like just for like convolution, because you're applying this 3x3 map. However, you may not actually hit you may not hit the edges on certain ones because of you're actually going 3x3 through like your model, but you will actually miss like the edges by itself. So this will allow like the model to actually go over the image data and actually make it the same size as the original image from like the convolution layer. Because usually convolution layer, you'll probably lose if you just have like a regular like stride of 1, and if you don't actually use like any padding, you'll probably reduce the degree of the image by like a size of 1. So like if you have a 32x32 image and you just apply a convolution layer without padding, you'll get a 28x28 layer. But if you actually add padding to like a padding of size 2, or I think that they call it, I think it's valid. Valid will actually make it the same size, so that you'll actually have your 32x32 image just going through like that layer. But then like once you go to that match point, it'll reduce dimensions there. And then the match point is sort of the same thing, except for you have to apply the kernel size and then strides also. Actually, the weights will actually deal with that. So the convnet this is sort of like my model that's created, or the model that you'll create. So this has initial shape of 28 by 28, which is pretty much the image size. That's the same as the one in the Keras set. You apply the convolution layer first. In this case, you have to pass in the weights and biases. So your weights are going to sort of be like your slope values, and then your biases are going to be your B value and like a function or in a 2D function. And then you apply match pool. And it's sort of a rinse repeat process before. You pass in new weights, and then you just do the match pooling layer after that. And then you do another convolution, and then you do match pooling, and then you reshape the data to actually figure out what the actual, or what it actually is categorizing it as. So here you see how I define my weights. So in the weights, you'll apply the kernel size. In this case, I was using a 5 by 5 kernel. This is like the input layer, which is just 1 at the start. You see, and then here's the output layer, so 32. So in the next layer, you have an input, like you have your kernel size of 5 by 5. You have your weights that are coming in, or your nodes that are coming in, or from your hidden layer, which is 32, which is the same as the output from here. And then you pass in what you want coming out. So in this case, I want 64. And so this is sort of a rinse repeat process where you have your 5 by 5, and then you have your 64, because 64 comes from here, and I just multiply it by 2, so I want 2 more, or times 2 more nodes coming out, or from the hidden layer from here. And then finally, when I want to put my model back together, actually also, you see here, I have the 4 times 4. What this is actually how like the dimensions have been reduced in the image. So this is just now it went from down from a 28 by 28 image to a 4 by 4 image, and then I'm just applying, just multiplying it by the final weights, and then this is the amount of neurons or classification things, and then I'm passing it out to my output to see what the results are. So these are pretty much all like the different values that are actually going into the results. Yeah, wait, what did I even do? Okay, there you go. Going into the results, into the actual final answering of whether or not like it's a cat or a dog, or in this case, if it's a 0 or a 1, 2, 3, etc. And then the same thing, you pretty much set up your model with all these things. You pretty much define like your cost function, which in this case I'm using the softmax again, and then passing in the labels and what I want to actually classify it as. You have your optimizer, which is again Atom, and then you have your accuracy scores, your correct model, and then in TensorFlow is just you're initializing your TF global variables, so all the variables I set up there. And then I'm starting my TensorFlow session, and this is where all of the machine learning happens, or like when the model actually starts running, and actually inits, or when you run session.run.init. Cool. And then the rest is just the TensorFlow backend taking care of the rest, and training the data model for you and updating all the values. So is there any?
Where do you have the batch, the epochs, sorry?
I actually just replaced it with terminology. If you see up here, instead I just use this training iters, which is 100,000, and then I use this this step function. So while it's actually under here, it'll just keep on replicating the process until it gets here, and so step just increases 1 at a time. So instead of doing that, I'm doing it like this, and then pretty much every single epoch is when the step modulus display step is equal to 0, and then I have display step up here to be 20. So every single time it sees 128, yeah, like 20 times, it will actually be like one epoch.
Can you go down
Yeah.
to the iteration? Yeah, so every time it happens,
I check whether or not.
around.
So every single time the step size, so every single time it sort of does the same process where it's checking like the 128 images. But after 20 steps of doing that, it will be one epoch because I have this step that starts at 1, and when 20 modulus 20 is equal to 0, or when step modulus display size is equal to 0, I'll actually do my loss, accuracy, and summary score, and actually like write that out to the screen. So that's sort of like it's a fancy way of doing an epoch. I just didn't use that terminology here.
Where do you have the optimizer, what you had add-on?
Yeah, I was using the Atom optimizer.
Okay.
Yeah, so TensorFlow is sort of weird where you set up everything beforehand, and then you pretty much set up you initialize your global variables or get everything pretty much prepared, and then you pretty much take that and then pass it into your sets.run to actually start the actual learning process, or you're running your model. It's not like top down, which is really it's very interesting.
And basically, carrots are calling all these functions in the background for you.
Exactly, but it's pretty much abstracted from you, which is very nice for when you're actually trying to learn. And I think that's, I think it's called Deep Learning DLPJ4, and Java does like the same sort of thing. There's other ones in R that sort of like does that. It's more like R stylistic, which makes it really nice and actually getting started in this type of stuff. Well, that's pretty much all I had. Just one other thing. Well, I guess not to show it, but it's gonna just show like that TensorFlow actually has this really cool logging process.
Can you squash the reset of window?
Oh yeah, I don't even know what happened. Can I? Oh, can I just clear it, or does that go too far up? Again. Is that better? I guess, yeah, I can make it work. I just wanted to show that TensorBoard actually has a really good logging sort of thing that you can actually do. So I actually just ran a model. It's off the side. Just allow. Then where did I put my browser? Huh.
Okay, so it's
Yeah, yeah, I guess we got rid of it.
interface.
Yeah, so when you're actually working with TensorFlow, which is actually really nice, I just realized I took it out for some reason. You can actually save your actual progress, or your summary of like your reports of like how your actually model actually performs. And then you have pretty much access to all so you can pretty much set up, so like if you're running like something like linear regression or like something like that, you can actually set up like the scalars and all like the functions and like the processes in your like loss function, and seeing how like your actual model performs. And then you can actually also download it from here and actually just change it. So this is actually why I think that our TensorFlow is so great, is that it comes with this nice interface where you can actually test your things. I don't know why I got rid of the setup, because I just ran it. But yeah, so like you can do if you're doing like image processing, you can like set up your images and see how like it actually like manipulates your images throughout the whole process. Or if you're doing something with audio where you're actually trying to like find like certain like wavelengths or something like that, or like common trends, you can like actually store it here and such on. Or you can do your graphs, distribution, histograms, sort of like that sort of thing. You all have access to that here, and then you can easily download it as a CSV file or PDF, so that you can actually inspect it in something like R or whatever your statistical background is in. So I just wanted to point that out because that was actually a cool resource that I actually found while going to a tutorial at PyCon or Pi Bay Area. So yeah.
Can you show an actual run of the model? How long does it take?
I mean, I still have a model on here of the same thing. Already did. I could just do Python. Actually, let me see what's, can I change this really fast?
So this H5, it's already a model where you...
Yeah, so I actually, exactly. Yeah, so beforehand I already trained the model, and I actually have it here. It's number class pro.h5. I ran this around for, I think, an hour or 30 minutes beforehand getting here. So yeah, I mean, that's another thing. Obviously, running it on a MacBook Pro is not the best thing. Usually you want to have like a desktop computer or like set up some like something in the cloud or Amazon cloud and run it up there, so you don't actually have to pretty much be deactive from your model or like from your computer, so you can actually still be working on this sort of stuff and actually going through it while it's actually running, so you can just get the results and actually be running on it. Otherwise, because it's not a short process. It actually takes time to actually run all these like complex computations, like how many times I'm actually multiplying and applying like matrix multiplication is time consuming. But yeah, so usually you'll want to save your model as an H5 so that you can actually, or that's how you'll actually be able to use your model in future projects, or just like to actually classify images in the future, or like if you're like satisfied with your model, or just that's how you'll actually do it. You'll save it as an H5 file, and then you'll pretty much just run it into or like pass that model back into another script, which will actually test or into the same one if you have like parse or something like that, where you're actually taking arguments. This is sort of like how TensorFlow's image recognition example actually does it. They actually give you their model. They just have you download their model, and then you can pass in any image and it'll classify it for you. I mean, it's a good way to get started, but it's sort of like abstracted away of like actually creating the model. So I think that's one thing that they do, but they do have the like sort of like a mini like minced like how to actually get started course on their website also. But yeah, once you have the model, or actually I can just sort of like, so like when you have like a model, or actually you sort of saw earlier, I will just do this one. So you see this is Keras, as you can see, or I'm using my Keras one, so pretty much you'll see something like this, where, oh, it's not, can I? Okay, yeah, I just want to see, so you're sort of like seeing how it's like computing like the or like the loss and like the accuracy score and stuff like that as it's going on. I mean, this isn't like as it's going, it's not like 100% accurate. It's just like, oh, I'm doing something. But like you'll see after, and at least it gives you the estimated time. So like in this case, I'm running, I think I had it set up to do 12 epochs. So as you see, every single one is around 90 seconds to do. And this is sort of a small demo sample sizing of this sort of thing. So this is why you need a lot of computing space. So yeah, I see it's going over, it wasn't set up so that it would go over 60,000, but like it has to see every single data point in the training set, so.
This is the first epoch.
Mm-hmm. Yeah.
We're gonna have 12 of this.
Yeah. That's why I had the model already set up, but yeah.
Can you use the model, the existing model, to run it on the test data set?
Yeah, you can actually, yeah, you can combine it to actually get it sort of like to improve like that model that you already have. You don't actually have to start off from new every single time you do it. But I don't have it set up that way. I just have it for like testing.py, where it's pretty much if I just run testing.py, it'll just take that like given model, and then it'll take one or two things and actually make the prediction on it. I wanted to change it so you can actually see a little bit better where actually what number is actually predicting, but in this case it predicted a 7 for it. As you see here,
yeah, all of them are very small.
Yeah, except for this one. Yeah, where this one's pretty much great, like right on the money. This is the only one. So that's sort of like the things that you're. So I was saying this one pretty much has a 100% chance to be right, and the case is this is the actual one that we wanted, which was 7, which is the position here. I sort of wanted to make it so that it actually showed the number, but I didn't put the index on there.
So each number there, it's digit 1, digit 2.
Yeah, it's like 0, yeah, 0, 1, 2, 3, 4, 5, 6, 7, yeah. And then, yeah, and then these are pretty much the prediction results for like each one. And you see like all these are pretty much 10 to the negative 15 times like whatever like that percentage is in standard or scientific notation, whereas this one is exactly 1. So we would make the assumption, or like the model pretty much perfectly predicted that this one is 1.
What is in the testing type?
It's actually really short. So actually let me open up and
Is there a way to run the model on all of the test data set? I don't know how many digits are.
I just did.
And then like getting a compound accuracy value of the model.
Oh, you mean, so that's sort of when you're actually training it. So like every single epoch, it actually, like that's what the accuracy score gives you. So like it'll train on like all like your training data, and then your test split will be like what gives you the accuracy score afterwards. So like after you like, it'll pretty much create sort of like a makeshift model while doing it, and then like on that model that's created, it'll like test those things on that and then check it like on like the thing while it's actually running, and that's where your accuracy is given from. Is that what you mean?
Well, partially. So he mentioned overfitting. So during the learning process, what you see is what it thinks about the learning set of input data. And if you have overfitting, which means that what you mentioned, that it just starts to stupidly just remember the images themselves and don't learn how number 9 goes, or a 0 is a round thing. So it doesn't learn that, but it just remembers the images. That's the overfitting. Then you might get to very high accuracy during the learning, but then when you test your model on the testing data set, it performs poorly. So that's what I would wonder, how would you run this last step when you want to verify
yes.
on a larger data set?
Okay, yeah. So usually, yeah, you would have your train test split, or like you wouldn't actually use everything. So usually you would take 0.33 or like 30. If you have like a large data set, you'll take 33% for your training data. You'll take 33% for your testing data, and then you'll run that again on that extra 33%. Or you'll like divvy up like how much you're actually doing your training and testing on based off like how much data you're doing, and then you test it on like unique like or like things that it hasn't seen later on. So that's like the sort of process that you go on there. Yeah, and then also for overfitting, you see here I have this dropout. This just means that you're pretty much ignore the training, or pretty much the, I guess, yeah, training on 25% of the data sets, so you don't like update 25% of like the actual weights in there. This is so it doesn't actually just memorize, or just like, it helps with like not memorizing trends and stuff like that, because you're only changing a certain portion of the data every single time. So like one time it may be like bad, or like the first model may not be as good, like, but you don't have to change every single point that time just because everything's bad, just to like memorize that, oh, this is bad on like here, over here on this image, so I gotta change this one, or like this kernel just for that image. But Instead, it pretty much says, okay, my score wasn't that great. Let me try to play around with some, or like a portion of the values in this data set and see how that does and how that actually worked with our model. So that's what the dropout of 0.25 and 0.5 does. Usually you want to have a smaller dropout towards the beginning, because that's where you're getting more of your common strains, and then like as you get later on further into your algorithm, you're getting more like concise like actual results. So you don't want to, you can just get rid of most of them. You don't have to change as much as them. Yeah, it's
partially because of the dropout, and the convolution helps as well.
Exactly, yeah. So the convolution in max point helps a lot, just because if you're already dimensional reducing it, just to actually find like, you're finding like values in like areas, and then you're passing in like the weights. So like, if you have like a rotated image, because of you're doing like this sort of like process where you're actually going through and finding like common trends and like just like areas, and then you'll have like this feed forward layer at the end. You'll find like the same like portion of a 7 that's on like the top as on the bottom, because that number will still be there, or like that common trim will still be somewhere in the neural network. That's actually just like saying, okay, lining up saying, oh, this is a 7 or something like that, or like in that case. So this is why especially with convolution layers, you don't actually have to do that much data processing beforehand to making sure like your data is actually clean. You're like everything's to scale. You don't have to normalize your data as much as you would have to do in other cases. Also, I didn't mention these are all grayscale. This data set uses gray tone images. You don't have to do that. The only thing that you have to do if you're using color images, instead of using just one data point, you're pretty much going to have 3 times as many points, because of you have your red, green, and blue points. And then if you're going to use alpha, whatever reason, you would actually have to pass that in. But usually you would just gray tone your image to make it easier.
Or maybe you grayscale it before.
Yeah, exactly. That's what most people do. But yeah, that's like one processing, and then just reducing your image size to be like a standard height and width for every single image. Yeah, that's pretty much what I have.